All right, continuing our discussion of Chapter 2, we left off here and how at a regional level the amount of water in the area can affect the climate. Obviously, it can in terms of water, but it also can affect temperature. So we have this desert versus this tropical area in the Amazon, and so there's clearly a lot more water here, and that, of course, results in a lot more vegetation, and that vegetation through the process of evapotranspiration is, you know, during the day at least, constantly releasing water into the atmosphere. So you're going to have much more humid air here, and the air here is much more dry. And so, we scroll down for a second, we see an analogous situation here between an area that was forested and one that's cleared, which is essentially kind of comparable to the desert. In the forested region, excuse me, you get a much more latent heat loss. And latent heat loss is the exchange of energy, the exchange of heat with little or no change in the temperature, or less change, you might say. So all that humidity in the air allows the air to absorb heat energy with less of a change in temperature. Whereas when you have really dry air, when there's heat being given off from the surface of the earth into the um, air, it results in more what's called sensible heat loss, where there is a change in temperature. Those air molecule temperature changes more radically than in the humid area because all that moisture in the air absorbs the heat, but the temperature doesn't change nearly as much. This all comes back to the heat capacity of water, and that is it takes a lot of energy to change the temperature of water, and so it's able to absorb heat without its temperature changing a whole lot. So basically, you get more extreme temperatures in your desert climate, your dry climate, than in your very humid climate. In the tropics, the temperature in a typical day might range somewhere between basically the 70s to 90s, whereas in your desert it might go from the 60s well into the hundreds. And so the air temperature changes. And again, we see comparable things with vegetated areas and then after they're cleared. All right, so let's talk about variation over time. Um, and so it happens, of course, seasonally due to the rotation or the tilt of the Earth and the fact that the Earth is tilting around the sun, because you have times of the year when the northern hemisphere is pointed towards the sun, basically our summer, and you have the summer solstice on June 21st when you're getting the longest days and the most tilt relative to the sun. Then in the fall and the spring, you have the equinoxes where the days are equally, the night and day are equally long. And again, even though the Earth is tilted, the axis is now parallel to the sun's axis. And then in the winter solstice, when the northern hemisphere is tilted away and you have your shortest days, um, and of course, you tend to have your colder weather here and your hot weather here. So the tilt of the Earth and the rotation of the Earth around the sun influences the seasons, and is related to the curvature of the Earth, that the equator, again, the sun is typically hitting directly on, but as you go to the poles, the sun is coming in at an angle, which means less sunlight per unit area at the poles. Now, even around the equator, though, where the sun is hitting most directly fluctuates through the year, such that, of course, at the summer solstice, um, when the northern hemisphere is tilted towards the sun, the most direct sunlight shifts towards the north at about 23.5 degrees north. And then in the equinoxes is when the sun is going to be most directly hitting the equator. But then in the winter solstice, it's going to shift down south of the equator. So essentially where the sun is most directly hitting, it hovers around the equator, but it does shift north and south with the seasons. Um, and this essentially shifts. We talk about there generally being a low pressure system at the equator, but that low pressure system will shift a bit north and south as is shown in this graph here. Um, and the South American one gets more precipitation um, um, in the earlier and later parts of the year, whereas in the middle of the year it gets less because the low pressure system has essentially shifted north and is now over this part where it's getting rainy, and then in the wintertime it's shifted down here. All right, aquatic systems have a seasonality, particularly cooler areas, because let's look at the summer. Now in the summer you'll get what we call thermal stratification, where the upper surfaces, what's called the epilimnion, is warmer, and the hypolimnion, the deeper parts of the lake, are cooler, and that warm water just kind of sits on top of the cool water, and the transition between them is known as a thermocline. In tropical areas where you have lakes, that's what you're pretty much going to see throughout the year. But where you have a colder season in temperate areas, as you get into fall, the water will cool down and you'll tend to get sort of an equalizing throughout the whole lake. And on windy days, you'll tend to get what's called a turnover, where there's mixing of the water between the depths. Um, this turnover is beneficial because in the summertime, the depths, the hypolimnion, can basically get very low in oxygen or even become anoxic, where there's no oxygen. Let me rewrite that, anoxic. And so what happens is the turnover will mix up, will take oxygen from the surface and take it to the depths. It also tends to bring nutrients from the bottom and bring it to the surface. So it kind of equalizes conditions of not only temperature but oxygen and nutrients. And then if you're far enough north, the surface, of course, will get cold enough to where it freezes and you'll get a layer of ice on that pond. But then in the springtime, it melts, things equilibrate, you'll get turnover again, and then the next summer you'll get this thermal stratification that occurs. All right, another change that occurs over time, and this is on a time scale, as you can see, from about 3 to 8 years more or less, is what's called El Nino. And El Nino is a change in the Pacific primarily, but it has implications throughout the globe. Let's go down here for a second. So the normal condition in the Pacific is to have low pressure systems in the western Pacific, which helps to pull water and wind currents from the east to the west. And you tend to get warmer or colder water coming from the south, from the north and the south. And so you can see the surface temperatures here tend to be a little cooler than average and warmer in other areas. What happens during an El Nino year is the low pressure system shifts to the eastern Pacific. The cold water that would be coming down from the north and up from the south doesn't essentially reach the equator, and instead you have water and winds coming from the west to the east, and so the eastern Pacific really heats up. And so this has significant impacts on regional climate. It tends to bring more, let's move on here, it tends to bring more moisture to the desert southwest because the winds are coming this direction now. It tends to make the southeast a little wetter and also cooler. Other areas, though, tend to get much drier than they would be otherwise. And you can see even parts of Africa, not particularly close to here, are also affected somewhat to a certain extent. The La Nina is sort of a coming back to the normal conditions, and when it shifts back, it often has a very strong effect, a very extreme low pressure system, which is really drawing water and wind across the ocean. The last El Nino peaked at about 2010, 2011. It gets the name, which means the child, and the child they're talking about is Jesus, because it tends to kick in around at the end of the year around Christmas time. Okay. All right, so when we look at climate over long periods of time, we see that it changes. Okay, and here we're looking at the average global temperature going back 600 million years, a long time ago. Um, and so you can see it sort of going up and down, but then we generally have these sort of warmer periods and these cooler periods. Um, but within those, of course, there's variation. And let's shift down here. This is looking at basically the same record, but going back a little further. These cool periods are characterized by having what we call ice ages. All right. That doesn't mean there's ice or an ice age throughout this time, but it is characterized by alternating periods of cooler and warmer climates, weather, and during those cooler periods, you tend to get an ice age. Um, we are in a period now where this is happening, but you can see there's long stretches throughout the Triassic, Jurassic, and Cretaceous. There's long periods where it was just relatively warm. Again, fluctuating some, but no ice ages were occurring. Um, so within a period of ice ages, you'll have periods of cold and warm. And when you have those cold periods, you do have what's called a glacial period where there's a lot more ice present on the Earth. And then in between glacial periods, you have what's called interglacials, and that's what we're in right now. The last glacial period reached its maximum about 18,000 years ago. Um, the interglacial periods last about 23,000 years. But you can see, so here's essentially the recent interglacial period we're in. Within it, of course, there's some warmer and some colder periods as well. Um, so here's looking at long-term record. Again, this is going back 450 million years. And again, we can see um, periods of warmer and colder periods. And of course, a shift in the ice. So this ice image is a little sort of flipped around because the periods of maximum or more ice are down low here, and the periods of less ice are up high here. And so as you can see, there's a really strong correlation between temperature and there being less ice, and during cold periods, there being more ice present. Um, Now, you can see these are estimates of temperature and or change in temperature. And so there's sort of this baseline reading, and then there are periods when the temperature is getting cooler and the periods when the temperature is getting warmer. Um, Now we have um, thermometers only date back at best to the 1700s. So it's really only in the recent past that we've been doing direct measurements of the temperature. So for obviously hundreds of thousands of years ago, there was no one here with thermometers keeping track of temperature. So you may wonder how we do this, how we get these estimates from the past, and it has to do with oxygen isotope ratios. There, of course, you know about isotopes from chemistry, and you can have isotopes with extra neutrons, and they're known as heavy isotopes. And so O16, oxygen 16 is the typical isotope, but there's oxygen 18, the heavier isotope, and it's present on the Earth. Um, and when you look at the precipitation, um, the deposition of rain and snow, the amount of the heavy isotope in that rain and snow varies over time. During warmer periods, there's essentially more of the heavy isotope, and during cooler periods, there's less of it. And so what happens is, so you look at this ratio of, oxygen 18 to 16, and they're not showing it on this graph, but essentially during these warmer periods, you'll have less of the O18, and during these cooler periods, you'll have more. And so there's a pretty good correlation between them. And so that's how we get our estimates of the change in temperature.